do in the book. 49, let's see, we start with
X squared plus X.
x
49 plus Y squared.
x squared plus xy plus y squared equals 7. Going to cross the x-axis, show that the tangents to the curve at these points are parallel. And what is their slope? So it'll cross the x-axis when y equals 0. So we want to plug in y equals 0. So that takes care of that. We get x squared equals 7. Is that right? So we're going to get a positive or negative square root of 7.
Yes.
And so we want to find the slope of the tangent line when x is square root of 7. That sound right? So, and then we have y 0. So it's going to be plus or minus square root of 7, comma 0 are 2 points. So from here, we're looking for a derivative. So we're going to do implicit differentiation. So that's going to be 2x. We got a product rule, first times derivative of the second, plus second times derivative of the first. And then the derivative of y squared is 2y to the first times y prime. And the derivative of 7 is 0. So we can keep the y prime terms here. And we'll move the others to the other side. Does that look okay? We'll factor the y prime out here, leaving x plus 2y. So we'll get y prime is going to be negative 2x minus y over x plus 2y. Okay, so far? And we want to find, now we want the slope at those points, is that right?
Yeah.
What do we, find a mistake?
No, you didn't. I see. I'm pretty sure I see where we went.
So y prime, now we're plugging in,
Yeah.
just do square root of 7, 0.
You're plugging in.
So that'll be a negative 2 square root of 7, that's going to be 0. That's going to be square root of 7, that's going to be 0. I think negative 2 is one of ours. And then if we plug in the negative square root of 7, we'll get negative 2 times negative square root of 7 is 2 square root of 7 over negative square root of 7. That's still negative 2, I think, right?
Yeah.
So either way, we get negative 2.
We plugged it in wrong. We plugged it into Y.
Calculus was good.
Yeah.
Evaluation, not so much.
It's always the basic stuff.
Anything else?
I think that's it.
All right, then let's see what we got on tap for today. Let's start with the derivatives of exponential and logarithmic functions. So this is 3.9 in our book.
It's the 13. We love jumping from 3 points.
So I don't know how many conflicts we have. We're ready to test on Friday. So we just kind of have the place to ourselves, except that I think everybody else in the world has stolen my idea of testing on Friday. So I think there's AP Stats and AP Biology are both testing on Friday. So why not make it a party and throw in BC Calculus to that mix as well? So my thought is to do it again on Friday at 8 to 10 in the morning. Does that work for everybody except for Austin? Or no? What time is Hogshead doing his?
Hogshead's doing his from 8 to...
He's doing his early in the morning too. I know there's some other kids in stats also. Well, not maybe in BC. I don't know. If there's a conflict, we can work it out. I'm going to be here all day Friday anyway. So if you want to do your stats test first and get a snack or take a break or whatever, and then come back and find me in my room, you can take it in here and we can do it that way, or make some other arrangement if that feels like it's too much to do in one day.
Okay. Are we getting a review tonight now?
Not yet today. There'll be a review out of your book today, and then the actual review I think is tomorrow.
So can we get that today since we get it Thursday and then do it the night before the test? Yeah.
I mean, I usually do it
Let's be honest here.
I do it both. I do it 2 times. Like I do it once to turn it in, and then do it again for actual review.
So we know that the derivative of e to the x is just itself. So to take the derivative of something that's not as nice, like say a to the x, we first recognize that we can write a as e to the natural log of a power. True?
Yes.
Because exponential base Euler's number, logarithm base Euler's number of inverses, it's just going to give you back to a. So then we rewrite the a to the x as e to the natural log of a to the x. You with me there? And then knowing that when you raise a power to a power, you multiply those exponents, still haven't done calculus yet. So we're going to get e to the x times the natural log of a. So now there's our e to the u, and the derivative of that we know is e to the u, the same thing back, times the derivative of what's multiplying the x, or multiplying what derivative of the exponent, which is going to be just natural log a. And so that, remember, was just our a to the x. So the derivative of anything other than base e is this annoying same exponential back times the natural log of whatever that base is, which is true in e to the x, but in e to the x, the natural log of e is just 1, so it works out really slick. So, for example, the derivative of 5 to the x is, yeah. Okay. I mean, it's not bad, it's just kind of irritating. But okay, now that's all we can do. So, in a similar fashion, we can figure out the derivative then of the natural log. So if we say that y is natural log of x, then if we exponentiate both sides, right, we get that e to the y is equal to e to the natural log x, which is just x. Okay? Now, if we do a little implicit differentiation here, the derivative of e to the u is going to be e to the u times du, and this is what we're really looking for, is that derivative of natural log x. That's our claim. On the other side, we have the derivative of x is just 1. So solving for the y prime, we get 1 over e to the y. But we said y was natural log x. It's just 1 over x, which is what we said. So the derivative of natural log x is just 1 over x.
Did we prove this last year, or is it just a thing? I don't remember proving it myself.
No, I don't think we do. And really, I don't know if this truly qualifies as a proof. I mean, it's a proof as long as we know what the derivative of e to the x is. We didn't really ever prove e to the x either. You can do it. It's just kind of painful because you have to, you know, you have to do the f of x plus h minus fx over h with exponentials, which you can do, but I think it's easier just to believe it in this case. So let's see, can we ask the interesting question? What is the slope of the line? What is the slope of the line tangent to y equals natural log x that passes through the origin? Oh, what a great question. I think we should do a picture. With your finger in the air, what does y equal natural log x look like? Nice. Okay, so it's going to go through this 0.10, and it's going to do something like that. This is really slow growing. So there's our natural log x. Now somewhere there's going to be all the tangent lines to this curve. And even right there's one that's going to go through the origin. I'm not sure where that's going to hit the logarithm curve. That's part of our challenge. Does that make sense? So we're trying to find the slope of the line tangent to that curve that goes through the origin. So how do we find that slope is the question. What's that? Well, we know that's the derivative, so dy dx is going to be 1 over x. So that's definitely going to be the slope. We don't know the x. That's the challenge. So what do you think? So this is one way to get the slope of that tangent line. What's another way, not involving the derivative, of getting the slope of the line between these 2 points? Yeah, so I'm going to do slope formula, but same thing, yeah. So what should we call that point since we don't really know what it is? Oh, how about x comma natural log x, since that's what the y is equal to? Does that make sense? And we also have the origin. So the slope, another way of getting at the slope, besides this 1 over x, is to say it'll be y2 minus y1 over x2 minus x1. Is that okay? So I guess if those are both expressions for that same slope, they must equal each other. So however you want to do this, cross multiply through by x. You're going to get eventually natural log x is 1, is that right? So x is going to be e. And then our slope, because remember we're trying to find the slope of that tangent line, is going to be, oh, what a great question that was. Okay? What if we want the derivative of a logarithm that's not a natural logarithm? So what do you do for the derivative of a logarithm some other base? What is it? How do you change that? So we want to change a base. So we're going to change that to a natural log somehow. Do you remember how to do it, or should we? Oh, very good. Do you remember that, or do you want to see it? Let's see it. So here's the way to do this. We haven't done this in recent memory. It's easy to forget. So we can, our goal is to convert this to a natural logarithm. So we can write the corresponding exponential. A to the y is x. You okay with that? That's that fundamental relationship between logarithms and exponents that you got to know. Then we can now take the natural log of both sides, because that's the logarithm we want. Okay. Then we use that property logarithms bring that y out in front. So that y was our original log base A of x. So we're going to go back and get that by itself. So we'll divide that natural log A to the other side. And so that's our conversion. We're going to make it into a natural logarithm by just taking the natural log of whatever it was, and you kind of have this extra annoying constant that is there that divide by natural log of A. Just like when we differentiated a to the x, we multiplied by that natural log A. With a logarithm, we convert it to a natural log x by dividing. And so then, what this becomes is the derivative of natural log x over natural log a, or maybe in your mind or something, you imagine pulling that constant out, that 1 over natural log a constant out, times the natural log of x. So the derivative of a constant times a function is the constant times the derivative of the function, which is going to be 1 over x natural log a. Yep. Okay. So one thing to notice is we do not gain domain through differentiation. So just to be careful, we do not gain domain through differentiation. Sometimes you might lose a number in your domain if the derivative doesn't exist there. But we start out with, say, f of x is equal to natural log of x. Well, as we write that there, so looking in the background is, what is the domain of f?
X is greater than 0.
Yeah, is that okay? So our domain is just x greater than 0. So when we then take the derivative, and we say f prime of x is 1 over x, we don't say anything, but what's the domain of 1 over x?
Well,
Everything but 0. Well, but not if it's coming from this derivative. So yes, it's true that if this was not a derivative, if this was just, so the distinction is, if we just said f of x is 1 over x, its domain is everything except for 0. But if this is coming from differentiating the natural log of x, then its domain, we can't gain all of that negative values of x. The domain is still going to be x greater than 0. So it's not divided to 0, but you don't gain the negative somehow. We don't ever write that down, but that's true. So somewhere in the back of your mind, maybe you should have a warning bell go off when you do that. So remember, if we're going to take a derivative of some massively ridiculous logarithm function, use your properties of logarithms first. So don't be in a rush to try to use your calculus. So if we take the natural log of, and we go say x to the 5th times the square root of x, maybe 4x minus 3 all over, say maybe x, let's go 2x plus 7 to the 3rd, and that's all in our logarithm, and we're interested in g prime of x. Don't jump in there and start doing product rule, quotient rule, chain rule, and all that stuff, because that is a mess. Instead, we'll use all of our clever logarithm properties first. So how might we do that?
The log of the top minus the log of the bottom.
So log of the top, I'm going to write that anticipating where we're heading, minus the log of the bottom. So far, so good.
So you can also break apart the top part.
Log of the product. So that's going to be sum of the logs. And finally bring those exponents I heard in front. So 5 natural log x plus 1/2 natural log of 4x minus 3 minus 3 natural log of 2x plus 7. So now, after all this, we have decomposed this as much as we can, or expanded it as much as possible. Now we have made our path to differentiation way easier, and that's definitely worth it. So it'll be 5 times
4 over x.
so we'll just call it 5 over x. And how about the next one?
It's, it comes out,
It's gonna be chain rule.
it's gonna be a chain rule, so you get 2 over 4.
So I'm going to do it in stages. You have the 4x minus 3, the du there, and we can cancel that. Okay? And similarly here. 2 goes up there. So I guess at the end of the day, we got 5 over x plus 2 over 4x minus 3 and 6 over 2x plus 7. Okay? Okay, so let's go on and talk about logarithmic differentiation. Okay, so if we have something like, say, y equals x to the sine x power. So usually we do this when you just have a function raised to a function power. Our book will sometimes use this idea even when you just have like a really, really messy exponential. So our book will use it maybe if we're trying to find the derivative of, say, x times the square root of x squared plus 1 all over x plus 1 to the 2/3 power. So let's maybe come back to the green one, but for the y equals x to the net sine x, remember how to do this? You don't do this very often, so it's easy to forget. Take the log of both sides. So we'll take natural log y, natural log x to the sine x power. This is helpful because, yeah, and that's the whole key. We want to make that into a product rule rather than something else that we have no idea what to do, that doesn't follow any rules. Now we can do implicit differentiation. So the derivative of natural log y is 1 over y prime. And on the other side, we're going to have to do a little product rule. So sine x times. Good. Plus natural log h times cosine x. So we're going to have to multiply that y to the other side. And should we just call sine x over x? You okay with that? And then I don't know the great way to write this. Which one you put in front is not going to look good. And then at the end we go back from the y to the x to the sine x. So we're going to get finally y prime is x to the sine x times sine x over x plus our natural log x cosine x. Okey-doke. Yeah, you want to do that one?
Sure.
Go ahead. I think that's a good one to do on the board.
Ooh, my green.
My extra long blue is good. Oh no, it's not. It's over here.
Going like mine.
Instead of just give it to us. Yeah.
Here you go.
Do you agree? Looks like we did.
Saved by Austin.
Nice. Saved by Austin.
Yeah, can I say?
Good save.
You gotta double check the map over and over to try and pick up the mistakes you make. And you
Okay.
still make a lot.
So here's
Yeah.
we're going to kind of get a preview of where we're headed a little bit here. I'm going to give you a problem, and you're welcome to stay up on
Yes.
the board and tackle this one. So we're going to say the spread
Oh,
of blue
I'm just gonna-
let's say spread of a rumor, and LHS is modeled by R of X equals, say, 100 over 1 plus e to the 3 minus t power. So I'm going to ask you some questions here. So A, can we estimate the initial number of students, the initial number of students, what shall we say, who know the rumor, or start the spread, know the rumor.
At what
And
point?
then
I think it's
B,
just the start.
then we want to know how fast
That's the beginning.
is the rumor spreading.
Oh, no, that's
After, and so we'll say that R is the number of people that
10 people.
now have heard the rumor.
Yeah.
Number of
Yeah,
people
E is like 2.7. Yeah, and
who
so
have heard the rumor.
27.
And we will say T is the time in, what do you think? Hours, minutes, seconds? We'll say minutes.
We'll put it even in call it decades.
Okay, so after, we'll say 3 minutes. And
That's what I thought.
then the next question is the really tough one. When is the rumor spreading the fastest?
Ooh. So what's the max? What's the derivative? I remember this.
So this is actually known as this is a logistic growth curve. We'll talk about this a lot more down the road here. So one of the properties you can see is that if you take the limit as t goes to infinity of this R of, I'm going to say R of t.
It gets
I
very
guess I should have said R of t. So what happens as t gets really, really big to this e to the 3 minus t?
That just gets closer to 1.
So he's
Yeah, so this will actually, it'll get close to 0.
Oh,
Yeah.
I was talking about the whole
Because you'll get e
bottom.
to, so this, just this part of it will go to 0. And so the number of people who know the rumor is going to be that 100.
That's what I thought.
And the limit as t goes to, it's kind of hard to run back time, but if we go to negative infinity, then what does that approach? Says,
Zero.
yeah, because now this becomes positive, and this gets bigger and bigger, it's going to get huge. So 100 over something that's growing large without bound is going to go to 0. So you're going to get something that's going to have horizontal asymptote to the left of 0 and horizontal asymptote to the right of 100. And so then you're going to get something that you'll see eventually is going to look something like this. So this logistic growth is supposed to be like a better model for growth functions than just exponential. Because very few things can grow exponentially forever. So this shows exponential growth initially, and then it levels off. So this is sometimes called the carrying capacity. It's like the maximum sustainable population, or in this case, the maximum number of people that could hear this rumor. All right, don't leave you much time. See what you can do with this.
So do we have something? Well, do you guys think that we can get through this?
So you're talking Friday too, huh?
Yeah.
Yeah,
Totally.
yeah, but I don't know how many like, it's only BC that I'm testing. So, those kids are
Oh, wait.
lost in it.
What number are you doing?
I'll go at 8 in the morning, but you go ahead. I'll tell my guys to go to yours first. then they can see some type of number.
Yeah, even one is fine. Yeah, I'm doing 8
Also
and
through
30.
this T, they just write like that, just part of the one to that, just one, and they just see the one. Yeah, so you guys do that again. I don't know if that'll work. What would it? Which is 1 to the n equals 61. Yeah, so you can just say it is also something.
It's like, that's hearing it from my table now.
You're like, I want to do the same thing.
And he really watches that, like, it's all right. So he's like, they look at that and stuff, and so he's like, you did it all great. You know, there's a reason for that. Because from the people that know you better, I just love people.
What? I got it. I get B, I guess. I didn't get the C.
We didn't get to C, which is the really, really hard part.
Okay.
But we'll get to it one day.
Okay.
It's not critical for right now. We'll talk about these later.
Will it be on the test? Is this on the test?